Okay, hi, thanks everybody for being here. And well, I'm aczid. Aaron is my real name. I also do other stuff besides this, and this is just sort of a hobby and things I got involved in over the last year. See how far I can take it. I think I've sort of well, covered the basics and maybe some new stuff for you. And so this is how this is our example program. I've put all this stuff in this package for you if you want to follow along. Will also be on the last slide if you want to play with it later at home. So this is our little binary, and the idea is that you can normally not read the function show password. This is basically our job of how to make a binary. This will output an ELF binary on Linux, and we're going to investigate some tools on how to debug it and see what else we can do to make it harder later on. And the idea is that the flag hexer is set to 0, and you can never reach it from the normal program execution, but if you use a debugger you can somehow make it to show password. The idea is from now on that we will not have the source code, so we can see using some tools what's going on. This is debugging. This is what is output. Structurally, an ELF has a header that describes the addresses within the file of the program header table, which describes the segments that follow, the text segment, data segment, and read-only data segment. Text segment is in this case in code, and then we have data that is mapped on the stack or heap. And the section header table refers to these segments and names them as sections. This gives you bigger information, names of what is the function, and they also have a strings table to tell you what their name is, and you can see more about the program than you would. But the section header table is optional, and you can strip it, as was explained by the last speaker. Here's what we can see from the output if we don't, by statically examining the output we can see the strings, and we can also already see the encrypted string below the format string, and now I can run the HITR2NDB2012 data box. And we can also see the function that gets called memfrog. And from here we can already get a good idea of what's going on in the binary and what we have to debug in it. Another tool we can use is LDD to see which dynamically linked libraries the program is linked against. In this case we have only libc, the other ones are special. We have VDSO, which is used to virtualize system calls in the Linux kernel. This actually lives in the kernel. And we have the Linux LD.so, the dynamic linker, which will load in other dynamic libraries from the binary. And on Linux is actually the interpreter, similar to a script interpreter like Python or Bash, that is used to run the ELF binary on Linux. Now here we have readelf. This is the common tool to see the layout of the schematic that I showed you earlier. It will show you all the information about the different sections, headers, all the different sections, what their names are, how they are mapped into memory. And really ELF is all about how a program is mapped into memory before execution continues. And then we have object dump, which will also let us see the whole assembly with all the debug information if it's present. And we can use it as a dead listing to reverse engineer the binary and crack it. And the most ghetto way to do that on Linux is using XXD. You can just edit the binary in Vim, run XXD over all the lines, and it will produce an assembly listing. Then we can hex edit the binary by hand, and then reverse the process with XXD-R. And then we'll have hex edit the binary as we wish. This is really general, but people can use it to debug our binary and make a cracked one that will work for them. Then we have strace. This will do log all the system calls that the binary makes internally, and all the libraries also make system calls, because the only way to really interface with the kernel is to make system calls. And this is what makes everything work. This is a lot of output, but very detailed. You can see exactly what happens at the start of a binary, how it's mapped into memory. First the dynamic linker gets loaded, then the binary itself, which starts with ELF. So X7F and then ELF, and then the rest of the binary is read into string, and the required areas are mapped into memory, the stack, the heap, and then at some point the actual entry point is reached, and we start with write. It's basically like a hello world program. and then it gets killed because we don't have the hexar flag set yet. And a more high-level view we can have with ltrace. This shows all the library calls, and in this example it only uses libc and only one function from it. But we can see in quite clear detail what is called from libc, and this is more useful to quickly analyze what's going on in a bigger program. The mother of all debuggers, as mentioned before, is GDB on Linux. On Linux is the mother of all. It's not really an awesome debugger, but it works fine. And as you can see, it's only 4 steps to win at our example program. If you've never done this, I really recommend you play around with my example program, easy.c, and do this and see how powerful it feels to actually control the process in memory. Then there's also the procfs. It was also shown before using the maps. And we can get a lot of information, including the original exe and the file descriptors. This is how it would look. These are actually, the exe is actually symboling to the original binary that's used. And the maps show the memory regions as they are mapped into memory. This can also provide you information for reverse engineering, debugging, and currently runtime binary injection. And now we get to the fun part. I'm sorry, I'm kind of hurrying along. Is there any questions so far? Or is there anything unclear that you'd like to get into more detail into? This is all clear. This is basically how we work with binaries on Linux. The fun stuff is what we can use in GCC to produce code that's harder to read, and the map page is actually helpful enough to inform us what flags in GCC make code hard to debug. If you look at the map page and search for debugging impossible, you'll find some of these features. The most common one is static. It takes all the library calls and puts them in the binary itself, so you don't need the libraries on the system anymore. And this will produce a bigger binary and has a lot of code that's not really relevant to your program, so it becomes more of a needle in a haystack challenge. Omitting the frame pointer will remove the information that the GDB can use to see what stack frame you're in. So the call stack becomes a bit more hard to reconstruct in your mind and in the program itself, of course. And unrolling loops is not actually an optimization here, but we can use it to, because it implies fweb and frename registers, and these also obscure the code output. They make it less structured, but it still works because the binary itself doesn't really care about debugging information and keeping the memory neatly organized. Or renaming registers doesn't matter to the binary. It would matter a lot to us if suddenly the purpose of registers is completely non-conventional. So look at the map page for more about what the stuff does. And then we have stripping, which will remove the debug output. As you can see, the number of section headers that are created and the number of strings in the binary goes down if we use strip. And there's also strip, which removes a bit more, and then we are left pretty much without anything to debug the binary with. This is what the GCC map page means with debugging impossible. But why stop here? It is sort of the default and the standard to have a statically linked binary and strip it. Then pretty much nobody will want to touch it unless they have access to tools like Hextrace or HITR2NDB2012. But those cost a lot of money and are not open source. They're sometimes free. Yeah, that's not really the way we want to play this game. We can do a bit better than just stripping. I think that having no bad information is better from our point of view than having no information. We have more information to confuse the reverse engineer with. So I have this program called troll.c. And what it does is it basically trollfuscates the ELF structure, technical term coined by my friend. And it changes few fields in the header, and it overrides a few choice sections in the binary with junk. And it will strip the section header, override the section header table itself, so you can't even find them in memory. The punchline in this one is that there are no program headers in this file. This can't be right, because program headers are essential. They have to be in the file. Somehow readelf gets confused, and we mess up its day. So this ends the static part of anti-debugging, compile options, and now we get to more dynamic stuff. Traditionally, it's packing or encrypting your memory image. This is very popular on Windows, but not so common on Linux. There's one tool that's very common, UPX, but it's not really hard to crack. So this is more of a conceptual idea of what we want to do, and I've made a very ghetto example here that you can inline into your C code, include it. What this does has a little dummy stub. The idea is that this stub, the entire stub, will be included at the top of the binary, and it will look right to the end to libcsu init, which hopefully will be right after main. So between this dummy and libcsu init, all the text section code that is present in the binary and created by the user will be decrypted using memprob instruction system shit. The memprob library call again. Before and after the memory page has to be protected to be written to using mprotect, and later on the write capability has to be removed again. And this has the following output. This is not really what we want as a reverser. It's very hard to make anything of this because it doesn't mean anything. And actually, these are not valid instructions. That's where they're annotated as bad. So, good start for little work. And another simple thing we can do as a C programmer is to make our process non-dumpable, prevent it from ever dumping a core. This would be useful information to a reverser because we can have access to all the map memory and see what's going on there. Also, the text segment will be plainly visible and can be loaded into the debugger or analyzed by itself. It's easy, a good start. And a very common trick that is actually pretty old school is to ptrace ourselves. It was also already introduced what ptrace is, but the kernel has a limitation that you can only have a process be ptraced once. So if you ptrace ourselves and it comes back negative, then there's a good chance that we're being debugged by ptrace. This used to be like one call, but since Ubuntu introduced the ptrace scope, we have to define which process is going to ptrace us and then call the ptrace. So we spawn a child here, and we let the child trace us. Just before we started, we set ourselves to be dumpable and identify the ptracer process. Then we let it run, and after it's done, we check the return status, and we set ourselves non-dumpable just before. And this is pretty effective, but what happens here? We can preload a C library function and make ptrace return 0 always, and then this entire protection is defeated. It's very useful to override C function in this way for debugging or anti-debugging, or anti-debugging in fact. So this is an anti-ptrace trick. But yeah, we don't want people to do this, so we can check the environment variables through the env pointer. This is what comes after the main count, argc count and argv arguments. And to the audience that's paying attention, why am I not using getenv and strcode?
You could do the same thing.
Exactly, right. You can do the exact same thing and overwrite what it's doing. So we have to do it by hand in C, and this will basically work. And a really silly trick that seems to be pretty much unknown is that we can hide from procfs and hide all this nice output. And we can hide from all the system process monitoring utilities that people rely on. They rely on it way too much, in fact, because we can just migrate our process several times a second, change our PID, and change our process name. And it will be exceedingly hard to actually debug this. And
good luck.
Yeah, very good luck. In fact, I myself have not been able to find a way to debug this properly. This kill that you see here is meant to confuse strace, because it will somehow assume that your binary has crashed, which is pretty logical, but we can ignore the zigzag fault signal. So this is a good way to annoy things that try to debug it. And yeah, I'm actually pretty scared by this. Please don't use this for anything unethical. So with our tools we profit. This is the output of many of the things I showed you, a few more. And our ptrace thing, and the LD end checker is in series, which will not run if we have any LD preloads, environment variables, and will not run in GDP. And all the other tools will not really understand that this is actually an L file. And even some crashes were unearthed in unstrip, which attempts to put back the missing debug information in the strip binary, and readelf, which we already covered. Unfortunately, their invalid reads are not really useful, but still entertaining. And IDA is even confused.
Wow.
This happens after 6 pop-ups, but no go. Yeah, take a picture. And how do we go on from here? We can use, we have to go into the kernel, because PocketFS is useless, and all these library calls to C can be hidden. We can statically link it, and we can strip it, and we can obfuscate the code. We have to go a level higher or deeper, depending on your view, and see what's going on from a more concrete perspective. And system-tab is an interface to do just that. It allows you to instrument the kernel without writing actual kernel modules. And it's pretty simple scripting language, and not as likely to actually have any negative effects, but you still can crash your kernel. And this is a simple example to show you sort of how the language looks like and what it can do. This would be, I guess, the way to continue on with the ProcFS maliciousness. What I'd like to have covered, or what we should probably cover next time, is how to write a better packer. There's a lot of information about this in the Windows world. How we can create fake disassembly by jumping in between instructions and hoping that the disassembler will see it as a legitimate jump and try to disassemble from there. When it will be misaligned, then it will appear as junk or assembly that does something else than we are actually doing. We can exploit code caves in the binary, so if we have a large section of non-operational instructions, or no-op, or we have code that has never reached in a normal run, we can put our code in between there. We can spread out payloads in little segments, and we can jump from one to another, back and forth, and hopefully we can confuse IDA to not show this graph, or have a circular graph, something that's hard to debug, even more still. We can use nanobytes, which are a way of replacing every branch instruction with interrupt call, which then is handled by an interrupt call, a table lookup, which then continues on from there. So for every branch instruction, we have an interrupt. This triggers the jump from the interrupt handler through its lookup table to the actual branch that is called. This also makes debugging harder because the interrupt is also used for debugging itself. And we can virtualize our code by inventing our own instruction sets, or we can perhaps build something on LLVM. This is an area for more research later. And that's all I have. So let's wrap it up.